Hello and welcome. Tonight, we journey together to a world that has captivated human imagination since the very first stargazers lifted their eyes toward the heavens. Jupiter, the wandering star that ancient peoples watched move slowly against the fixed backdrop of constellations, has been a symbol of kingship, of divine authority, of the very greatest powers that govern existence. Named for the supreme deity of the Roman pantheon, the father of gods and ruler of the sky, this magnificent planet has inspired countless myths, guided navigators across uncharted seas, and sparked the curiosity that eventually led humanity to send spacecraft across the vast gulf of space to study its swirling clouds up close. So settle in, let your breathing slow, and allow your mind to drift as we explore everything there is to know about the largest planet in our solar system. Long before telescopes revealed Jupiter's banded atmosphere and churning storms, human beings recognized this bright wanderer as something special. To the unaided eye, Jupiter appears as one of the brightest objects in the night sky, outshone only by the Moon, Venus, and occasionally Mars when the red planet swings close to Earth in its orbit. This brilliance made Jupiter impossible to ignore, and ancient civilizations across the globe developed rich traditions surrounding this celestial beacon. The Babylonians, those meticulous observers of the heavens who lived in the fertile crescent of Mesopotamia thousands of years ago, tracked Jupiter's movements with remarkable precision. They called the planet Marduk, naming it after their chief deity, the god who had brought order out of chaos in their creation myths. Babylonian astronomers recorded Jupiter's position night after night, year after year, developing mathematical models that could predict where the planet would appear in the sky far into the future. These ancient scholars understood that Jupiter took approximately 12 years to complete one circuit through the constellations of the zodiac, spending roughly 1 year in each constellation. This 12-year cycle became deeply embedded in Babylonian astrology and influenced how they interpreted omens and portents related to kingship and the fate of nations. The ancient Greeks inherited much of this Babylonian astronomical knowledge and wove it into their own mythological framework. They associated the bright wandering star with Zeus, the king of their gods, the wielder of thunderbolts who ruled from his throne atop Mount Olympus. The connection between the planet and the supreme deity reflected Jupiter's commanding presence in the night sky. Just as Zeus was the mightiest of the Olympians, so too was his celestial counterpart the most impressive of the wandering stars. Greek philosophers, like Aristotle, contemplated the nature of the planets, believing them to be perfect spheres embedded in crystalline shells that rotated around the Earth. Though this geocentric model would eventually be overturned, the Greek systematic approach to understanding the cosmos laid important groundwork for later astronomical discoveries. When Roman civilization rose to prominence, they adopted much of Greek mythology and astronomy, renaming Zeus as Jupiter and transferring all the associated celestial symbolism. The Romans saw Jupiter as the protector of the state, the god who watched over Rome's destiny and granted victory in battle. Temples dedicated to Jupiter, Optimus Maximus, Jupiter the best and greatest, stood at the heart of Roman cities, and generals celebrating military triumphs would ascend the Capitoline Hill to offer sacrifices at his altar. The planet Jupiter, shining steadily in the night sky, served as a constant reminder of divine oversight and cosmic order. But the Romans and Greeks were far from the only peoples to develop rich traditions around this brilliant planet. In ancient China, astronomers of the Han dynasty and earlier periods tracked what they called the year star, recognizing its 12-year orbital period and incorporating it into their calendrical systems. Chinese astrologers associated Jupiter with the element wood and the direction east, weaving the planet into the complex system of correspondences that governed Chinese cosmology. The 12-year cycle of Jupiter's orbit may have influenced the development of the 12-year cycle of the Chinese zodiac, with its familiar sequence of animals representing each year. Hindu astronomers in ancient India knew Jupiter as Brihaspati, the guru of the gods and the lord of sacred wisdom. In Vedic astrology, which remains influential to this day, Jupiter is considered the most benefic of all planets, associated with good fortune, expansion, wisdom, and spiritual growth. The position of Jupiter in a person's birth chart was believed to indicate their capacity for learning, their relationship with teachers and mentors, and their overall luck in life. Temples dedicated to Brihaspati still receive devotees seeking the planet's blessings, and certain days of the week are considered particularly auspicious for Jupiter-related rituals. The Maya civilization of Central America developed one of the most sophisticated astronomical traditions of the ancient world, and Jupiter played an important role in their observations. Mayan astronomers tracked the planet's movements with extraordinary precision, recording its appearances and disappearances as it passed behind the sun from Earth's perspective. These observations were incorporated into the complex Mayan calendar systems and influenced the timing of religious ceremonies and political events. The Dresden Codex, one of the few surviving Mayan books, contains detailed tables tracking Jupiter's motion that demonstrate the remarkable mathematical sophistication of Mayan astronomy. Indigenous peoples of North America also observed Jupiter and incorporated it into their celestial traditions. The Pawnee people of the Great Plains, renowned for their astronomical knowledge, recognized Jupiter as one of the important celestial bodies that govern the rhythms of their ceremonial life. The Skidi Pawnee in particular developed an elaborate star-based religion in which the positions of celestial objects determined the timing of rituals and the organization of their villages. While the specific role of Jupiter in Pawnee tradition varied among different bands and time periods, the planet's brightness ensured it a place in their celestial observations. As European civilization emerged from the medieval period into the Renaissance, interest in the classical world revived, and with it came renewed attention to the planets and their mythological associations. Artists depicted Jupiter the god in countless paintings and sculptures, often showing him enthroned among clouds, thunderbolt in hand, eagle at his side. These artistic representations reinforced the connection between celestial and divine power, reminding viewers that the bright planet bearing this name was the cosmic counterpart of the King of Gods. The astrological traditions that had developed over millennia continued to assign Jupiter rulership over expansion, abundance, and benevolence. Astrologers considered Jupiter the great benefic, a planet whose influence brought growth, opportunity, and protection from harm. When Jupiter was well placed in a horoscope, it was thought to promise success, wealth, and happiness. These astrological associations, while not scientifically valid, demonstrate how deeply Jupiter had embedded itself in human consciousness as a symbol of the very best that the cosmos had to offer. Even the naming conventions that astronomers would later apply to Jupiter's features reflect this rich cultural heritage. When scientists began mapping the planet's moons and studying its atmosphere, they drew upon the mythology surrounding Jupiter, the god. The 4 largest moons bear the names of Zeus's lovers from Greek mythology: Io, Europa, Ganymede, and Callisto. Later discoveries would be named for other figures associated with Jupiter in various mythological traditions, creating a nomenclature that honors thousands of years of human storytelling about this magnificent planet. In literature and art of more recent centuries, Jupiter has continued to inspire creative works that blend scientific understanding with imaginative speculation. Science fiction authors have set stories on Jupiter's moons, imagining human colonies beneath Europa's ice, or research stations in orbit around the giant planet. Artists have attempted to capture the sublime beauty of Jupiter's swirling clouds and the dramatic vistas that might greet a traveller approaching this enormous world. Musicians have composed pieces inspired by Jupiter's majesty, most famously Gustav Holst's Jupiter, the Bringer of Jollity, from his orchestral suite The Planets, a work that captures something of the expansive, generous character that astrologers had long associated with this celestial body. The cultural legacy of Jupiter thus spans virtually all of human history and encompasses contributions from civilizations on every inhabited continent. From Babylonian astronomers carefully recording the planet's position on clay tablets to modern spacecraft sending back images of storms larger than Earth, Jupiter has been a constant companion to humanity's journey of cosmic discovery. This bright beacon in our night sky has inspired myths and religions, guided calendars and ceremonies, and sparked the curiosity that eventually led us to understand what this distant world truly is. Not a wandering god, but something perhaps even more wonderful, a planet of such immense size and complexity that it challenges our imagination to comprehend it. As we continue our journey tonight, we will explore how humanity's understanding of Jupiter transformed from mythological symbol to scientific subject. We will trace the story of the first telescopic observations that revealed Jupiter as a world with moons of its own, overturning ancient assumptions about Earth's unique place in the cosmos. We will descend through Jupiter's layered atmosphere, explore the hellish volcanic landscape of Io, swim beneath the frozen surface of Europa's ocean, and follow the spacecraft that have ventured across hundreds of millions of miles to study this giant planet up close. But for now, simply rest in the knowledge that when you look up at Jupiter in the night sky, you are seeing the same bright light that Babylonian priests watched from their ziggurats, that Greek philosophers contemplated from their academies, that Chinese astronomers tracked from their imperial observatories. Across all the ages of human existence, Jupiter has been there, a steady presence reminding us that we are part of something vast and ancient and full of wonder. Let your eyes grow heavy as we prepare to move forward in time, from the age of mythology to the age of discovery, when a simple improvement in optical technology would forever change what we knew about this distant world. Section 2, Discovery and Early Observations. The transformation of Jupiter from wandering star to world with satellites began on a cold January night in the year 1610, when an Italian mathematician and natural philosopher named Galileo Galilei turned a new instrument toward the heavens. The telescope, recently invented in the Netherlands, had come to Galileo's attention, and with characteristic ingenuity he had constructed his own version, improving upon the original design to achieve greater magnification. What he saw when he pointed this device at Jupiter would shake the foundations of how humanity understood its place in the universe. On the night of January 7th, 1610, Galileo observed 3 small points of light arranged in a line near Jupiter. He initially assumed these were fixed stars that happened to lie along the same line of sight as the planets. But when he looked again, on subsequent nights, he noticed something remarkable. The points of light had moved. They were not fixed stars at all, but objects that accompanied Jupiter in its journey across the sky. By January 13th, Galileo had identified a 4th point of light, and over the following weeks of careful observation, he determined that these 4 objects were orbiting Jupiter itself. The implications of this discovery were profound. For over 1,000 years, European astronomy had been dominated by the geocentric model inherited from ancient Greece, particularly the system elaborated by the astronomer Ptolemy in the 2nd century. In this view, Earth sat motionless at the centre of the universe, and all celestial bodies, including the sun, moon, planets, and stars, revolved around it. The discovery that Jupiter had moons of its own demonstrated that not everything in the heavens orbited Earth. Here was clear evidence that celestial bodies could orbit something other than our planet, lending support to the heliocentric model proposed by Nicholas Copernicus, in which Earth and the other planets orbited the Sun. Galileo published his observations in a small book titled Sidereus Nuncius, the Starry Messenger, which appeared in March 1610. The work caused a sensation throughout Europe. Some scholars embraced the new discoveries as evidence for the Copernican system, while others dismissed them as optical illusions produced by the imperfect lenses of the telescope. The Catholic Church, which had endorsed the geocentric model as consistent with certain biblical passages, would eventually condemn Galileo for his support of heliocentrism, forcing him to recant his views and spend his final years under house arrest. But the moons of Jupiter could not be unseen, and other astronomers with their own telescopes quickly confirmed what Galileo had observed. The 4 moons that Galileo discovered are now known as the Galilean moons in his honour: Io, Europa, Ganymede, and Callisto. These names were actually proposed not by Galileo himself, but by the German astronomer Simon Marius, who claimed to have observed the moons independently around the same time. Marius drew the names from Greek mythology, selecting figures associated with Zeus, the Greek counterpart of Jupiter. Io was a priestess whom Zeus loved and transformed into a cow to hide her from his jealous wife, Hera. Europa was a Phoenician princess whom Zeus, in the form of a white bull, carried across the sea to Crete. Ganymede was a beautiful Trojan youth, whom Zeus abducted to serve as cupbearer to the gods. Callisto was a nymph and hunting companion of Artemis, whom Zeus seduced and who was later transformed into a bear. Galileo himself had proposed naming the moons the Medicean stars, hoping to curry favour with his patron Cosimo de' Medici, Grand Duke of Tuscany. This name did not catch on, and today we use the mythological names proposed by Marius, though we credit Galileo with the discovery itself. The priority dispute between Galileo and Marius was one of many such controversies in the history of astronomy, where improvements in technology allowed multiple observers to make similar discoveries nearly simultaneously. In the years following Galileo's announcement, astronomers across Europe turned their telescopes toward Jupiter, confirming the existence of the 4 moons and beginning to track their orbital motions. The Danish astronomer Ole Rømer made particularly important use of these observations in the 1670s. Rømer noticed that the timing of the moon's eclipses, when they passed behind Jupiter and disappeared from view, varied depending on the distance between Earth and Jupiter. When Earth was closer to Jupiter in its orbit, the eclipses occurred slightly earlier than predicted. When Earth was farther away, they occurred slightly later. Rømer correctly deduced that this variation was caused by the finite speed of light. When Earth was closer to Jupiter, light from the eclipsing moon had less distance to travel and arrived sooner. When Earth was farther away, the light had to cross a greater expanse of space, causing a delay. By measuring this delay, Rømer was able to calculate the first reasonably accurate estimate of the speed of light, determining that it took light about 22 minutes to cross the diameter of Earth's orbit around the Sun. This was somewhat higher than the modern value of about 16 minutes, but it was a remarkable achievement for its time, and demonstrated that light, though incredibly fast, did not travel instantaneously. The telescopes of the 17th century were primitive by modern standards. with small lenses that produced blurry, distorted images surrounded by coloured fringes. Despite these limitations, patient observers were able to discern that Jupiter was not merely a point of light, but a disk with visible features. The Italian astronomer Giovanni Cassini, working at the Paris Observatory in the 1660s and 1670s, made detailed observations of Jupiter's appearance, noting the banded structure of its atmosphere and tracking features that rotated across the planet's face. Cassini discovered that Jupiter rotated remarkably quickly for such a large object, completing one rotation in just under 10 hours. This rapid rotation caused the planet to bulge noticeably at its equator and flatten at its poles, giving Jupiter a distinctly oblate shape that was visible even through the telescopes of the era. Cassini also observed and tracked a large oval feature in Jupiter's southern hemisphere, which may have been an early sighting of what we now call the Great Red Spot, though the historical record is not entirely clear on whether the feature Cassini observed was the same storm we see today. The Great Red Spot itself entered the historical record more definitively in the 19th century, when astronomers began making systematic observations of Jupiter's atmospheric features. This enormous storm, large enough to swallow Earth with room to spare, became one of Jupiter's most recognizable characteristics. Observers tracked its motion, noted changes in its color and size, and speculated about its nature. Was it a solid feature on Jupiter's surface? A gap in the clouds revealing something beneath? A storm system of some kind? The true nature of the Great Red Spot would not be understood until the space age, but its presence added to Jupiter's mystique as a world of dramatic and dynamic phenomena. Throughout the 18th and 19th centuries, improvements in telescope design allowed astronomers to observe Jupiter in ever greater detail. The invention of the achromatic lens, which reduced the coloured fringes that plagued earlier telescopes, produced sharper images. Larger telescopes gathered more light, revealing fainter details. Astronomers mapped the bands and zones of Jupiter's atmosphere, giving them names that are still used today: the North Equatorial Belt, the South Equatorial Belt, the North Tropical Zone, and so on. Spectroscopy, the analysis of light broken into its component wavelengths, provided new insights into Jupiter's composition. In 1863, the British astronomer William Huggins and his wife Margaret used spectroscopic techniques to study Jupiter's light, attempting to identify the gases present in its atmosphere. These early spectroscopic observations were difficult to interpret, but they marked the beginning of efforts to understand Jupiter not just as a visual object, but as a physical world with a specific chemical makeup. By the early 20th century, astronomers had determined that Jupiter's atmosphere contained ammonia and methane, gases that would be toxic to humans, but that made sense for a cold, hydrogen-rich world far from the sun. The development of infrared astronomy allowed scientists to measure the heat radiating from Jupiter, leading to the surprising discovery that the planet emits more energy than it receives from the sun. This excess heat, we now understand, is left over from Jupiter's formation and is slowly leaking away into space as the planet gradually contracts and cools. The discovery of additional moons beyond the original 4 Galilean satellites expanded our understanding of Jupiter's extensive satellite system. In 1892, the American astronomer Edward Emerson Barnard discovered a 5th moon, later named Amalthea, orbiting closer to Jupiter than any of the Galilean moons. Amalthea was tiny compared to the Galilean satellites and had escaped detection for nearly 3 centuries because of its small size and proximity to Jupiter's glare. The 20th century brought a flood of additional moon discoveries, as photographic techniques and later electronic detectors made it possible to find ever smaller and fainter objects. Jupiter's moon count grew steadily, revealing a complex system of satellites with diverse orbits. Some moons orbited close to Jupiter in nearly circular paths, aligned with the planet's equator. Others followed distant, elongated, inclined orbits that suggested they were captured asteroids or comets rather than objects that had formed alongside Jupiter. Today, we know of more than 90 moons orbiting Jupiter, making it the planet with the most known natural satellites in our solar system. The pre-space age understanding of Jupiter, built up over more than 3 centuries of telescopic observation, painted a picture of a giant world unlike anything else in our cosmic neighbourhood. Jupiter was clearly enormous, with a diameter more than 11 times that of Earth. It rotated rapidly, its 10-hour day driving powerful atmospheric currents that created the banded appearance visible through telescopes. Its atmosphere contained hydrogen-rich compounds like ammonia and methane, and it radiated more heat than it received from the Sun. 4 large moons and numerous smaller ones orbited this giant planet, forming a miniature solar system of sorts. But many fundamental questions remained unanswered. What lay beneath Jupiter's visible cloud tops? Did the planet have a solid surface somewhere deep within, or was it gas all the way down? What powered the Great Red Spot and the other storms visible in Jupiter's atmosphere? What were the surfaces of the Galilean moons like? Were they dead, cratered worlds, like Earth's moon, or did they harbour surprises of their own? Answering these questions would require leaving Earth behind and sending robotic emissaries across the vast gulf of space to study Jupiter up close. The space age was about to begin, and Jupiter would be one of its most important destinations. As you rest and let these thoughts drift through your mind, consider how much human understanding has grown since Galileo first glimpsed those 4 points of light near Jupiter. Each generation of astronomers built upon the work of those who came before, gradually assembling a picture of Jupiter that grew more detailed and more accurate with each passing decade. The journey of discovery that began with a simple telescope in 1610 would eventually lead to spacecraft orbiting Jupiter itself, sending back images and data that would have seemed like magic to Galileo and his contemporaries. Let the wonder of this accumulated knowledge wash over you as we prepare to explore how Jupiter came to be, how this giant world took shape in the swirling disk of gas and dust that surrounded our young sun more than 4 billion years ago. Section 3. Jupiter's place in the solar system. To understand Jupiter fully, we must journey back in time more than 4.5 billion years, to an era when our sun was young and our solar system was still taking shape. In those ancient days, the sun had recently ignited, beginning the nuclear fusion reactions in its core that would sustain it for billions of years to come. Surrounding this infant star was a vast disk of gas and dust, the leftover material from the cloud that had collapsed to form the sun itself. Within this protoplanetary disk, the seeds of planets were beginning to grow. The story of Jupiter's formation is intimately connected to the story of the entire solar system, and understanding how this giant planet came to be helps explain why our cosmic neighbourhood looks the way it does today. Jupiter was not merely a passive participant in the solar system's early history. It was one of the primary architects of the planetary arrangement we see around us, its immense gravity shaping the orbits and fates of countless smaller bodies. In the inner regions of the protoplanetary disk, close to the young sun, temperatures were high enough that only rocky and metallic materials could remain solid. Volatile substances like water, ammonia, and methane existed only as gases in these warm inner zones. Small particles of rock and metal collided and stuck together, gradually building up larger and larger bodies through a process called accretion. These rocky bodies would eventually become the terrestrial planets: Mercury, Venus, Earth, and Mars. But farther from the Sun, beyond a boundary that astronomers call the frost line or snow line, temperatures dropped low enough for volatile compounds to freeze into solid ice. This boundary, located somewhere between the present orbits of Mars and Jupiter, marked a crucial transition in the composition of the protoplanetary disk. Beyond the frost line, the solid material available for planet building included not just rock and metal, but also abundant water ice and other frozen volatiles. This meant that planets forming in the outer solar system had access to much more raw material than their inner solar system counterparts. Jupiter began its existence as a rocky and icy core, growing through the same accretion process that built the terrestrial planets. But because it formed beyond the frost line, where solid material was more abundant, Jupiter's core grew faster and larger than any body in the inner solar system. When this core reached a critical mass, estimated at somewhere between 10 and 20 times the mass of Earth, something dramatic happened. The core's gravity became strong enough to capture and hold onto the lightweight gases, hydrogen and helium that made up the bulk of the protoplanetary disk. Once this gas capture began, it proceeded rapidly. Hydrogen and helium from the surrounding disk flowed onto the growing Jupiter, adding to its mass and increasing its gravitational pull, which in turn allowed it to capture even more gas. This runaway growth continued until Jupiter had accumulated an enormous envelope of hydrogen and helium surrounding its original rocky icy core. The process may have taken only a few 100,000 years, a brief moment in astronomical terms, but it transformed Jupiter from a large rocky body into the gas giant we know today. The timing of Jupiter's formation was crucial for the rest of the solar system. Jupiter grew large enough to capture gas while the protoplanetary disk was still present, before the young sun's radiation and stellar wind had dispersed the remaining gas into space. If Jupiter had formed more slowly, the disk might have dissipated before the planet could capture its massive atmosphere, and Jupiter would have remained a large, rocky world rather than becoming a gas giant. The fact that Jupiter exists in its current form tells us that it formed quickly, within the first few million years of the solar system's history. Jupiter's rapid growth had profound consequences for the other planets. As the largest body in the solar system besides the Sun, Jupiter's gravity influenced the orbits of everything around it. One of the most significant effects was on the asteroid belt, the region between Mars and Jupiter, where millions of rocky bodies orbit the Sun. In the early solar system, this region contained enough material to potentially form another planet. But Jupiter's gravitational influence stirred up the orbits of bodies in this zone, causing them to collide at high speeds that shattered them rather than allowing them to stick together and grow. Jupiter effectively prevented a planet from forming in the asteroid belt, leaving behind the scattered remnants we see today. The influence of Jupiter extended even to the inner solar system, where the terrestrial planets were taking shape. Computer simulations of the early solar system suggest that Jupiter's gravity may have played a role in limiting the size of Mars. The red planet, despite being farther from the Sun than Earth, is much smaller than our world. One explanation for this is that Jupiter's gravitational influence depleted the region where Mars formed, leaving less material available for the growing planet to accumulate. Mars thus ended up as a relative runt among the terrestrial planets, its growth stunted by the distant but powerful influence of giant Jupiter. Some of the most dramatic chapters in Jupiter's early history involve the possibility that the giant planet did not always orbit where we find it today. The theory known as the Grand Tack hypothesis proposes that Jupiter formed farther from the Sun than its current position, then migrated inward through the protoplanetary disk before reversing course and moving back outward. This inward then outward migration like a sailboat tacking against the wind, could explain the several puzzling features of the solar system's architecture. According to the Grand Tack scenario, Jupiter migrated inward to roughly the present orbit of Mars, before the gravitational influence of Saturn, which was also migrating at the time, caused both planets to reverse direction and move outward. During its inward journey, Jupiter would have scattered or destroyed much of the material in the inner solar system, potentially explaining why the terrestrial planets are relatively small compared to rocky planets found in other star systems. The reversal and outward migration would have then allowed fresh material to flow back into the inner solar system, providing the raw ingredients for Earth and its neighbours to complete their formation. While the Grand Tack hypothesis remains a subject of ongoing research and debate, it illustrates how Jupiter's influence extended throughout the solar system, shaping not just its immediate neighbourhood, but regions hundreds of millions of miles away. The solar system we inhabit today is in many ways a product of Jupiter's gravitational sculpting, and understanding Jupiter's history helps us understand why Earth exists in its current form. Another important role that Jupiter plays in the solar system is that of cosmic guardian. The giant planet's powerful gravity acts as a kind of shield for the inner solar system, deflecting or capturing many of the comets and asteroids that might otherwise rain down on Earth and the other terrestrial planets. When a comet falls inward from the outer solar system, it may encounter Jupiter's gravitational field and be flung onto a different trajectory, sent back out into the cold depths of space, rather than continuing toward the Sun and the inner planets. This protective role was demonstrated dramatically in July 1994, when the comet Shoemaker-Levy 9 collided with Jupiter. The comet had been captured by Jupiter's gravity during a previous close approach and had broken into more than 20 fragments that were strung out like pearls on a string. Over the course of several days, these fragments plunged into Jupiter's atmosphere one after another, creating enormous fireballs and leaving dark scars in the planet's clouds that persisted for months. The impacts released energy equivalent to millions of nuclear weapons, and the scars they left were larger than Earth itself. The Shoemaker-Levy 9 impact was the first collision between solar system bodies that humans had ever witnessed, and it provided a vivid reminder of the violent processes that continue to shape our cosmic neighbourhood. It also demonstrated Jupiter's role as a cosmic catcher's mitt, absorbing impacts that might otherwise threaten the inner planets. While Jupiter's protective influence is not absolute and impacts on Earth have occurred throughout our planet's history, the presence of a giant planet in the outer solar system likely reduces the frequency of such catastrophic events. Jupiter also plays a role in the dynamics of the outer solar system, influencing the orbits of the other giant planets and the countless small bodies that populate the regions beyond Neptune. The gravitational interactions between Jupiter and Saturn helped shape the orbits of Uranus and Neptune during the solar system's early history, potentially causing these ice giants to migrate outward to their present positions. Jupiter's influence extends even to the Kuiper Belt, the ring of icy bodies beyond Neptune's orbit, and to the Oort cloud, the vast spherical shell of comets that surrounds the solar system at distances of tens of thousands of astronomical units from the Sun. The position of Jupiter in our solar system, roughly 5 times farther from the Sun than Earth, places it in a region where sunlight is about 25 times weaker than at Earth's distance. This means that Jupiter receives far less solar energy than our planet, and its cloud tops are bitterly cold, with temperatures around minus 145 degrees Celsius. Yet, as we noted earlier, Jupiter radiates more energy into space than it receives from the Sun, a testament to the vast reservoir of heat left over from the planet's formation that continues to leak slowly outward through its atmosphere. Jupiter orbits the Sun once every 12 Earth years, moving slowly against the background stars as ancient astronomers observed. Its orbit is nearly circular, with an eccentricity of only about 0.05, meaning that its distance from the Sun varies by only about 5% between its closest approach and its farthest recession. This relatively stable orbit helps maintain the gravitational balance of the outer solar system, providing a steady anchor around which the complex dance of planets and smaller bodies unfolds. The relationship between Jupiter and the Sun is closer than you might expect for two bodies separated by hundreds of millions of miles. Jupiter and the Sun actually orbit around their common centre of mass, a point called the barycenter. Because Jupiter is so massive, more than twice the mass of all other planets combined, the Jupiter-Sun barycenter lies outside the Sun's surface, about 1.07 solar radii from the Sun's centre. This means that the Sun actually wobbles slightly as Jupiter orbits, a motion that astronomers have used to detect giant planets around other stars by looking for similar wobbles. As you let your thoughts drift among these cosmic considerations, imagine the young solar system as it appeared more than 4 billion years ago. Picture the swirling disk of gas and dust surrounding the infant Sun, the countless particles colliding and sticking together, the growing cores of future planets accumulating mass in their feeding zones. See Jupiter as it crosses the critical threshold, its gravity suddenly strong enough to grasp the surrounding gas, its growth accelerating as it balloons into a giant world. Watch as its influence spreads outward, stirring the asteroid belt, limiting the growth of Mars, perhaps even migrating through the disk before settling into its current orbit. This ancient history, written in the orbits and compositions of the bodies that make up our solar system, tells us that Jupiter is not just the largest planet but one of the most important. Its formation and evolution shape the architecture of the entire solar system, determining which planets would exist, how large they would grow, and where they would orbit. The Earth on which we live, the moon that lights our nights, the asteroids and comets that occasionally visit our skies, all bear the imprint of Jupiter's gravitational influence. Rest now with this cosmic perspective, knowing that our solar system is an interconnected whole, each part influencing the others in a gravitational dance that has continued for billions of years. Jupiter stands at the centre of this dance, the conductor of an orbital symphony that includes every planet, moon, asteroid and comet in our Sun's family. Section 4. Anatomy of a gas giant, the atmosphere. Now we descend from the cosmic scale to examine Jupiter itself, beginning with the swirling clouds that form the face this giant planet presents to the universe. Jupiter's atmosphere is a world unto itself, a realm of violent storms and gentle breezes, of colourful bands and mysterious spots, of lightning bolts that dwarf anything on Earth, and winds that blow with speeds that would tear apart any human structure. To explore Jupiter's atmosphere is to enter a realm where familiar weather phenomena are amplified to scales that challenge the imagination. The first thing to understand about Jupiter's atmosphere is that there is no clear boundary between atmosphere and planet. Unlike Earth, where a solid surface provides a definite floor beneath the gaseous envelope of air, Jupiter has no surface in the conventional sense. As you descend through Jupiter's atmosphere, the gas simply becomes denser and denser, eventually transitioning into a liquid state without any sharp boundary. Astronomers define the top of Jupiter's atmosphere as the level where the pressure equals 1 bar, roughly the same as atmospheric pressure at sea level on Earth. Everything above this level is considered the upper atmosphere, while everything below is the deep atmosphere and interior. The uppermost layers of Jupiter's atmosphere are composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. These gases make up about 90% and 10% of Jupiter's atmosphere by number of molecules, respectively. But it is the trace components, the small amounts of other substances mixed into this hydrogen-helium envelope, that give Jupiter's atmosphere its colour and complexity. Ammonia is one of the most important trace gases in Jupiter's atmosphere. This compound, made of nitrogen and hydrogen, freezes into white crystals at the cold temperatures found in Jupiter's upper atmosphere, forming the bright white clouds that are visible in many regions of the planet. Ammonia clouds float at the highest altitudes of Jupiter's visible atmosphere, at pressures of about half a bar and temperatures around -145 degrees Celsius. When we look at Jupiter through a telescope, much of what we see is the tops of these ammonia ice clouds, gleaming white in the reflected sunlight. Beneath the ammonia clouds lies a layer of clouds composed of ammonium hydrosulfide, a compound formed from ammonia and hydrogen sulfide. These clouds are thought to have a brownish or orange colour, and they float at slightly higher pressures and temperatures than the ammonia clouds above. The ammonium hydrosulfide cloud deck is not directly visible from Earth, but its presence is inferred from models of Jupiter's atmospheric chemistry and from data returned by spacecraft. Deeper still, at pressures of several bars and temperatures approaching the freezing point of water, lies a layer of water clouds. Water is abundant in Jupiter's atmosphere, carried there from the icy bodies that contributed to the planet's formation. These water clouds are hidden from direct view by the layers above, but they play an important role in Jupiter's weather, driving convection and powering some of the storms that we observe in the upper atmosphere. The banded appearance of Jupiter, one of its most distinctive features, arises from the organization of these cloud layers by the planet's rapid rotation and atmospheric circulation. Jupiter spins on its axis once every 10 hours, the fastest rotation of any planet in our solar system. This rapid rotation, combined with the heat rising from Jupiter's interior, drives a pattern of alternating wind bands that encircle the planet parallel to its equator. The light-coloured bands are called zones, and they represent regions where air is rising from the depths of the atmosphere. As this air rises, it cools, and the ammonia and other compounds it carries condense into bright white clouds. The zones are regions of relatively high pressure at the cloud tops, where the rising air spreads out horizontally before eventually sinking back down. These bright stripes encircle Jupiter like ribbons wrapped around a gift, their creamy white colour reflecting sunlight back into space and giving the planet much of its visual brightness. Between the zones lie the darker bands known as belts. These represent regions where air is sinking back down into the depths of the atmosphere after rising in the adjacent zones. As the air descends, it warms, and the clouds that form during its ascent evaporate, revealing the darker, warmer layers beneath. The belts typically appear in shades of brown, orange, and reddish tan, colours that arise from complex chemical reactions involving sulfur, phosphorus, and organic compounds in Jupiter's atmosphere. The exact chemistry that produces these colours remains a subject of ongoing research, as the precise compounds responsible have proven difficult to identify definitively. The boundary between each zone and belt is marked by powerful jet streams, rivers of wind that flow around the planet at tremendous speeds. These jets blow alternately eastward and westward, with each belt zone boundary hosting a jet flowing in the opposite direction from its neighbours. Wind speeds in these jets can exceed 600 kilometers per hour, far faster than any hurricane on Earth. The jets are remarkably stable, maintaining their positions and speeds over decades of observation. though the clouds and storms embedded within them constantly shift and evolve. The absence of any solid surface on Jupiter means there are no mountains, valleys, or continents to disrupt these atmospheric flows. On Earth, our jet streams meander and shift as they encounter mountain ranges and temperature differences between land and sea. Jupiter's atmosphere, by contrast, flows smoothly around the planet with nothing to impede it, resulting in the remarkably uniform, banded pattern that has persisted for as long as humans have observed the planet through telescopes. This uninterrupted flow allows the bands to maintain their structure over centuries, even as individual storms and cloud features come and go. The most famous feature in Jupiter's atmosphere is undoubtedly the Great Red Spot, an enormous anticyclonic storm that has been raging in the planet's southern hemisphere for at least several hundred years. This colossal tempest is so large that Earth could fit inside it with room to spare, though the storm has been gradually shrinking over the past century and a half. When astronomers first began systematic observations of the Great Red Spot in the 19th century, it measured roughly 40,000 kilometers across, large enough to swallow 3 Earths side by side. Today, the storm has contracted to about 16,000 kilometers in diameter, still enormous by terrestrial standards, but noticeably smaller than in historical observations. The Great Red Spot rotates counterclockwise, completing one full rotation approximately every 6 Earth days. Winds at the outer edge of the storm blow at speeds approaching 450 kilometers per hour, while the center of the vortex is relatively calm. The storm is embedded in the south equatorial belt, positioned between 2 jet streams that flow in opposite directions. This location, caught between opposing currents, may help explain the storm's remarkable longevity, as the shearing winds on either side help maintain the vortex's rotation. The distinctive red color of the Great Red Spot has long puzzled scientists. The storm's clouds rise higher into Jupiter's atmosphere than the surrounding regions, exposing them to more intense ultraviolet radiation from the sun. Laboratory experiments have shown that ultraviolet light can break apart ammonia and other compounds in Jupiter's atmosphere, producing reddish-brown substances that may be responsible for the storm's coloration. The exact chemical composition of these chromophores, as the color-producing compounds are called, remains uncertain, but candidates include complex organic molecules, sulfur compounds, and phosphorus-bearing substances. The Great Red Spot is not the only large storm on Jupiter. The planet hosts numerous other oval-shaped vortices, some of which have persisted for decades. In the year 2000, 3 smaller white oval storms in Jupiter's southern hemisphere merged to form a single, larger storm, which subsequently developed a reddish colour and was nicknamed Red Spot Junior, or Oval BA, by astronomers. This storm, while smaller than the Great Red Spot, demonstrates that Jupiter's atmosphere is capable of producing long-lived vortices in various locations and at various scales. Jupiter's atmosphere also produces storms of a more transient nature. Bright white plumes occasionally erupt from the deeper atmosphere, punching through the upper cloud layers and spreading out before dissipating over days or weeks. These convective outbursts are powered by the heat rising from Jupiter's interior and by the condensation of water vapor in the deep atmosphere. When water vapor rises and condenses into clouds, it releases latent heat, just as it does in thunderstorms on Earth. This released heat provides additional buoyancy, driving the air even higher and creating the towering convective plumes that occasionally disturb Jupiter's otherwise orderly banded structure. Lightning accompanies these convective storms, just as it does in terrestrial thunderstorms. Spacecraft visiting Jupiter have detected powerful lightning flashes in the planet's atmosphere, some of them far more energetic than any lightning bolt on Earth. The Juno spacecraft currently orbiting Jupiter, has observed lightning flashes occurring primarily in the polar regions and on the night side of the planet, where convective activity appears to be most vigorous. The lightning is generated by the same process that produces it on Earth: the separation of electrical charges within turbulent clouds, followed by a sudden discharge that equalizes the charge imbalance. The polar regions of Jupiter present a dramatically different appearance from the banded equatorial and temperate zones. Instead of orderly stripes, Jupiter's poles are dominated by clusters of cyclonic storms arranged in geometric patterns. At the North Pole, a central cyclone is surrounded by 8 smaller cyclones arranged in an octagonal pattern. At the South Pole, a similar central cyclone is encircled by 5 peripheral cyclones, forming a pentagonal arrangement. These polar cyclone clusters were discovered by the Juno spacecraft and represent one of the most surprising findings of that mission. The polar cyclones are enormous by terrestrial standards, with diameters ranging from 4,000 to 7,000 kilometers, comparable to the continental United States. They rotate with wind speeds of up to 350 kilometers per hour and have remained remarkably stable since their discovery, maintaining their geometric arrangements over years of observation. How these cyclone clusters formed and why they maintain their specific configurations remains an active area of research, as no other planet in our solar system displays similar polar atmospheric structures. Above the visible cloud layers, Jupiter's upper atmosphere extends hundreds of kilometers into space, gradually thinning until it merges with the near vacuum of interplanetary space. This upper atmosphere, or thermosphere, is surprisingly hot, with temperatures reaching over 700 degrees Celsius at high altitudes. This elevated temperature is puzzling because Jupiter is so far from the Sun that solar heating alone cannot account for it. Scientists believe that energy from Jupiter's powerful auroras, combined with waves propagating upward from the lower atmosphere, may be responsible for heating the thermosphere to such unexpected temperatures. Jupiter's auroras are among the most spectacular in the solar system, far more powerful than the northern and southern lights that grace Earth's polar skies. These auroras are produced when charged particles from the Sun and from Jupiter's volcanic moon, Io, are funneled along magnetic field lines into the planet's polar atmosphere. When these energetic particles collide with atmospheric gases, they excite the atoms and molecules, causing them to emit light. Jupiter's auroras glow primarily in ultraviolet wavelengths, invisible to human eyes but easily detected by spacecraft instruments. The auroral displays on Jupiter are not merely beautiful, they also provide valuable information about the planet's magnetic field and its interaction with the surrounding space environment. The auroras trace out the shape of Jupiter's magnetic field lines, revealing the complex geometry of this invisible force field that extends millions of kilometers into space. Bright spots within the auroral ovals mark the magnetic footprints of Jupiter's largest moons, showing where field lines connecting the planet to Io, Europa, and Ganymede intersect the atmosphere. As we descend deeper into Jupiter's atmosphere, the pressure and temperature steadily increase. At a depth of about 100 kilometers below the visible cloud tops, the pressure reaches 10 bars, 10 times the atmospheric pressure at Earth's surface. The temperature at this level is around 20 degrees Celsius, surprisingly comfortable by human standards. Though the atmosphere's composition of hydrogen, helium, and trace amounts of toxic compounds would be instantly lethal to any unprotected human visitor. Continuing downward, the pressure and temperature continue to rise. At a depth of about 1,000 kilometers, the pressure exceeds 1,000 bars, and the temperature climbs to several hundred degrees Celsius. The hydrogen gas that makes up most of Jupiter's atmosphere behaves differently under these extreme conditions. becoming denser and more fluid-like, even though it is not technically liquefied. There is no sharp boundary between gas and liquid in Jupiter's atmosphere. Instead, the transition is gradual, with the hydrogen smoothly changing from a low-density gas to a high-density fluid as depth increases. The atmosphere of Jupiter is a dynamic, ever-changing realm where storms rage for centuries, winds blow at hurricane speeds, and lightning bolts dwarf anything on Earth. Yet for all its violence, there is a strange beauty to Jupiter's atmospheric patterns, a visual harmony in the alternating bands and swirling vortices that has captivated observers since the first telescopes were turned toward this giant world. As you rest and let your thoughts drift, imagine yourself floating among Jupiter's clouds, watching the great red spot rotate slowly beneath you, feeling the gentle tug of winds that have blown without ceasing for longer than human civilization has existed. Let the rhythm of Jupiter's atmosphere lull you towards sleep, the endless circulation of rising and sinking air, the patient rotation of ancient storms, the soft glow of auroras dancing at the poles. This is a world of perpetual motion, where the weather never stops and the sky has no end. A fitting realm for the king of planets. Section 5. Deep Interior and Core. Beneath the swirling clouds and raging storms of Jupiter's visible atmosphere lies a realm that no human eye has ever seen, and no spacecraft has ever penetrated. The deep interior of Jupiter is a place of extremes, where pressures reach millions of times the atmospheric pressure at Earth's surface, and temperatures soar to tens of thousands of degrees. To understand what lies beneath Jupiter's clouds, scientists must rely on indirect evidence: the planet's overall density, its gravitational field, its magnetic field, and theoretical models of how matter behaves under extreme conditions. As we descend through Jupiter's atmosphere, leaving behind the colourful clouds and entering the depths where no sunlight penetrates, the first major transition occurs at a depth of roughly 1,000 to 2,000 kilometres below the cloud tops. Here the pressure has risen to approximately 10,000 bars, and the temperature has climbed to around 5,000 degrees Celsius. At these conditions, the hydrogen that makes up most of Jupiter's bulk has transitioned from a gaseous state to a liquid state, though as we noted earlier, this transition is gradual rather than abrupt. There is no surface, no boundary where gas suddenly becomes liquid. Instead, the hydrogen simply grows denser and denser until it behaves more like a liquid than a gas. This liquid hydrogen layer extends deep into Jupiter's interior, growing ever hotter and denser as depth increases. The hydrogen in this region is molecular hydrogen, meaning that the hydrogen atoms are paired together in molecules of 2 atoms each, just as they are in the hydrogen gas we encounter on Earth. The liquid molecular hydrogen layer is thought to extend to a depth of roughly 15,000 to 20,000 kilometres below the cloud tops, where another remarkable transition occurs. At depths greater than about 20,000 kilometres, the pressure exceeds 2 million bars and the temperature rises above 10,000 degrees Celsius. Under these extreme conditions, hydrogen undergoes a phase transition unlike anything we can easily replicate in laboratories on Earth. The hydrogen molecules are squeezed so tightly together that they break apart, and the electrons that normally orbit individual hydrogen atoms become detached and free to move throughout the material. This creates a state of matter known as metallic hydrogen, in which hydrogen behaves like a liquid metal, conducting electricity and heat with remarkable efficiency. Metallic hydrogen is one of the most exotic substances in the solar system, and Jupiter contains more of it than any other body we know of. The metallic hydrogen layer is thought to extend from about 20,000 kilometres depth down to the planet's core, a vast ocean of liquid metal more than 40,000 kilometers deep. This metallic hydrogen ocean is responsible for one of Jupiter's most impressive features, its enormously powerful magnetic field. Jupiter's magnetic field is the strongest of any planet in our solar system, roughly 20,000 times more powerful than Earth's magnetic field at the cloud tops. This immense magnetic field is generated by electrical currents flowing within the metallic hydrogen layer, driven by the planet's rapid rotation and the convective motions that transport heat from the deep interior toward the surface. The process is similar to the dynamo that generates Earth's magnetic field in our planet's liquid iron outer core, but Jupiter's dynamo operates on a vastly larger scale and produces a correspondingly more powerful field. The magnetic field extends far beyond Jupiter's visible surface, creating an enormous magnetic bubble called the magnetosphere that surrounds the planet and its moons. Jupiter's magnetosphere is the largest structure in the solar system after the Sun's heliosphere, stretching more than 600 million kilometers in the direction away from the Sun. If Jupiter's magnetosphere were visible to the naked eye, it would appear several times larger than the full moon as seen from Earth, despite Jupiter's great distance from us. Within the magnetosphere, charged particles from the solar wind and from Jupiter's volcanic moon, Io, are trapped and accelerated to tremendous energies. These particles spiral along magnetic field lines, creating intense radiation belts that would be lethal to any unprotected human astronaut. The radiation environment near Jupiter is so harsh that spacecraft visiting the planet must be specially designed to withstand the bombardment of energetic particles. And even then, their electronics can be damaged by prolonged exposure. Continuing our imaginary descent through Jupiter's interior, we pass through the metallic hydrogen layer and approach the planet's core. The nature of Jupiter's core has been a subject of scientific debate for decades, and recent data from the Juno spacecraft has provided new insights that have challenged earlier assumptions. Traditional models of Jupiter's interior assume that the planet had a dense, compact core of rock and ice at its centre, similar to the core that would have formed first during Jupiter's accretion from the protoplanetary disk. This core was thought to have a mass of roughly 10 to 20 Earth masses and a diameter of perhaps 20,000 kilometres, sitting at the very centre of the planet like a seed at the heart of a fruit. However, measurements of Jupiter's gravitational field by the Juno spacecraft have revealed a more complex picture. The gravitational data suggests that Jupiter's core is not a compact, well-defined ball of rock and ice, but rather a dilute or fuzzy core that extends over a much larger region and is mixed with the surrounding hydrogen and helium. In this model, heavy elements are concentrated toward the centre of the planet, but are not sharply separated from the lighter elements above. Instead, there is a gradual transition from the hydrogen-helium envelope to a core region enriched in heavier elements. One possible explanation for this dilute core is that Jupiter experienced a giant impact early in its history, when a large planetary embryo collided with the young Jupiter and disrupted its originally compact core. Such an impact would have mixed core material with the surrounding envelope, creating the fuzzy core structure that Juno's measurements suggest. This hypothesis remains speculative, but it illustrates how Jupiter's interior may preserve evidence of dramatic events from the solar system's violent youth. The temperature at Jupiter's centre is estimated to be around 20,000 to 25,000 degrees Celsius, hotter than the surface of the Sun. The pressure at the centre reaches approximately 40 million bars, a pressure so extreme that it is difficult to comprehend. Under these conditions, matter behaves in ways that are challenging to model, even with the most sophisticated computer simulations. The core region, whatever its exact structure, contains a significant fraction of Jupiter's total mass of heavy elements, including rock-forming minerals, water ice that has long since melted and dissociated into its component atoms, and other compounds that were incorporated into the planet during its formation. Jupiter radiates about 1.7 times as much energy into space as it receives from the Sun, a clear indication that the planet has an internal heat source. This excess heat is primordial, left over from Jupiter's formation more than 4 billion years ago, when Jupiter accreted its massive envelope of hydrogen and helium from the protoplanetary disk. The gravitational energy released by this process heated the planet's interior to tremendous temperatures. Ever since, Jupiter has been slowly cooling, radiating this stored heat into space at a rate that will continue for billions of years to come. The cooling process is gradual because Jupiter is so large that heat takes a long time to work its way from the deep interior to the surface where it can be radiated away. Convection, the rising of hot material and sinking of cool material, is the primary mechanism for transporting heat through Jupiter's interior. The convective motions in the metallic hydrogen layer drive the dynamo that generates Jupiter's magnetic field, while convection in the outer molecular hydrogen layer helps power the atmospheric circulation that creates the visible bands and storms. As Jupiter continues to cool, it also continues to contract, shrinking by a tiny amount each year as the interior loses heat and the material becomes slightly denser. This contraction releases additional gravitational energy, which is converted to heat and helps slow the cooling process. The interplay between cooling and contraction means that Jupiter will remain a warm, active world for the foreseeable future, its interior churning with convective motions, and its magnetic field continuing to pulse with electrical currents. The deep interior of Jupiter is a realm we can never visit, a place where the conditions are so extreme that no material we know of could survive. Yet through careful measurements and clever theoretical modelling, scientists have pieced together a picture of this hidden world, a place of liquid metal oceans and fuzzy cores, of temperatures hotter than the sun's surface and pressures that crush atoms into exotic states of matter. As you drift towards sleep, let your imagination wander through these impossible depths, floating through the metallic hydrogen ocean, feeling the warmth of Jupiter's primordial heat, sensing the pulse of electrical currents that generate the mightiest magnetic field of any planet. This is the heart of Jupiter, the engine that drives its storms and powers its auroras, the hidden core of the king of planets. Rest now, knowing that even the most familiar objects in our night sky contain mysteries that challenge our understanding and inspire our wonder. Section 6. The Galilean Moons, Io. Beyond Jupiter's swirling clouds and deep interior lies a system of moons so diverse and fascinating that it constitutes a miniature solar system in its own right. More than 90 moons orbit Jupiter, ranging from tiny irregular fragments only a few kilometres across to worlds larger than the planet Mercury. But 4 moons stand out above all the rest, the 4 that Galileo discovered more than 4 centuries ago: Io, Europa, Ganymede, and Callisto. These Galilean moons are worlds unto themselves, each with its own unique character and its own remarkable story to tell. We begin our tour of the Galilean moons with Io, the innermost of the 4 and one of the most extraordinary bodies in the entire solar system. Io orbits Jupiter at a distance of about 422,000 kilometres, completing one orbit every 1.77 Earth days. This proximity to Jupiter has profound consequences for Io's geology, making it the most volcanically active body we know of. a world where eruptions occur continuously and the entire surface is reshaped on timescales of years to decades. When the Voyager spacecraft flew past Jupiter in 1979, scientists expected Io to be a dead, cratered world, similar to Earth's moon. The thinking was that a body of Io's size, roughly 3,140 kilometers in diameter, would have lost its internal heat long ago and would display a surface scarred by billions of years of meteorite impacts. What Voyager revealed instead was a world utterly unlike anything scientists had imagined. A surface painted in vivid yellows, oranges, reds and blacks, with not a single impact crater visible anywhere. The absence of impact craters on Io was the first clue to the moon's extraordinary nature. Impact craters accumulate over time on any solid surface exposed to space, so the lack of craters meant that Io's surface must be extremely young, constantly renewed by some geological process that erases craters as fast as they form. That process, scientists quickly realized, was volcanism on a scale unprecedented in our solar system. Io's volcanoes erupt continuously, spewing sulfur and sulfur dioxide onto the surface and into space. The Voyager spacecraft captured images of volcanic plumes rising hundreds of kilometers above Io's surface, fountains of material ejected with such force that they escape the moon's weak gravity and form temporary rings around Jupiter. Subsequent missions, including the Galileo spacecraft that orbited Jupiter from 1995 to 2003, revealed the full extent of Io's volcanic activity, documenting hundreds of active volcanic centers and tracking changes in the surface over time. The source of Io's volcanic heat is not radioactive decay, as it is for Earth, but rather tidal heating. Io orbits close to Jupiter, and the giant planet's immense gravity raises tidal bulges on the Moon, stretching it slightly toward Jupiter. If Io's orbit were perfectly circular, these tidal bulges would remain fixed in place, and no heat would be generated. But Io's orbit is slightly elliptical, forced into this shape by gravitational interactions with the other Galilean moons, particularly Europa and Ganymede. As Io moves around its elliptical orbit, its distance from Jupiter varies, and the strength of Jupiter's tidal pull changes accordingly. When Io is closer to Jupiter, the tidal bulges are larger. When it is farther away, they are smaller. This constant flexing of Io's interior, like repeatedly bending a paperclip back and forth, generates enormous amounts of heat through friction. The heat produced by tidal flexing is sufficient to melt rock in Io's interior, creating a global magma ocean beneath the moon's thin solid crust. The volcanoes on Io come in several varieties. Some are shield volcanoes similar to those found in Hawaii, broad, gently sloping mountains built up by countless lava flows over time. Others are more explosive, producing the towering plumes that Voyager first photographed. Still others are lava lakes, pools of molten rock that glow with temperatures exceeding 1,000 degrees Celsius, hot enough to be detected by infrared instruments on spacecraft hundreds of thousands of kilometers away. The composition of Io's lavas is predominantly silicate rock, similar to the basaltic lavas erupted by volcanoes on Earth. However, the surface of Io is coated with sulfur and sulfur dioxide, which give the Moon its distinctive coloration. Sulfur can exist in many different molecular forms depending on temperature, and these different forms have different colours, ranging from yellow to orange to red to black. The patchwork of colours on Io's surface reflects the varying temperatures and compositions of volcanic deposits across the Moon. One of the most dramatic volcanic features on Io is Loki Patera, a massive lava lake more than 200 kilometers across. Loki is the most powerful volcano in the solar system, radiating more heat than all of Earth's volcanoes combined. The lava lake periodically overturns as cooler, denser crust on the surface sinks and is replaced by fresh molten rock from below. These overturn events cause Loki's brightness to fluctuate in a roughly predictable pattern, allowing scientists to forecast when the next brightening will occur. Another notable volcanic centre is Pele, named after the Hawaiian goddess of volcanoes. Pele produces a distinctive red ring of sulfur deposits around its vent, created by the fallout from its volcanic plumes. The red ring of Pele is one of the most recognizable features on Io's surface, a vivid splash of colour against the moon's already colourful landscape. The volcanic gases ejected by Io's eruptions do not simply fall back to the surface. Some of them escape into space where they become trapped in Jupiter's powerful magnetic field. These gases form a donut-shaped ring around Jupiter called the Io plasma torus, a region of charged particles that glows with ultraviolet light. The plasma torus is continuously replenished by material escaping from Io, making the Moon a significant source of particles for Jupiter's magnetosphere. Io's interaction with Jupiter's magnetic field also produces intense electrical currents that flow between the Moon and the planet. These currents, carrying millions of amperes of electricity, create bright spots in Jupiter's auroras at the locations where the magnetic field lines connecting to Io intersect the planet's atmosphere. The Io footprint, as this auroral feature is called, is one of the most prominent features in Jupiter's ultraviolet auroras and provides a visible link between the volcanic moon and its giant parent planet. Despite its hellish conditions, Io holds a certain stark beauty. The vivid colours of its volcanic plains, the graceful arcs of its eruption plumes, the glowing calderas visible against the moon's night side, all combine to create a landscape unlike anything else in our experience. Io is a world of fire and brimstone, a place where the ground itself is constantly being remade by forces beyond human scale. Yet it is also a world that teaches us about the power of tidal forces, the diversity of volcanic processes, and the unexpected ways that moons can interact with their parent planets. As you rest and let your thoughts wander across Io's tortured surface, imagine the heat rising from countless volcanic vents, the sulphurous gases billowing into the black sky, the distant bulk of Jupiter hanging overhead, its bands and storms visible in exquisite detail from this close vantage point. Io is a world of perpetual transformation, where nothing stays the same for long, and the only constant is change. Let the rhythm of its eruptions, the pulse of its tidal heartbeat, carry you gently towards sleep. Section 7. The Galilean moons, Europa. Moving outward from Io, we come to Europa, a moon that could scarcely be more different from its volcanic neighbour. Where Io is a world of fire, Europa is a world of ice, its surface covered by a frozen shell that gleams white and smooth in the reflected sunlight. But beneath that icy exterior lies what may be the most promising environment for extraterrestrial life in our solar system. A global ocean of liquid water, kept warm by the same tidal forces that drive Io's volcanism. Europa is slightly smaller than Earth's moon, with a diameter of about 3,122 kilometres. It orbits Jupiter at a distance of roughly 671,000 kilometres, completing one orbit every 355 Earth days. Like Io, Europa is locked in a gravitational dance with the other Galilean moons, and this interaction keeps its orbit slightly elliptical, generating tidal heat in its interior. But Europa is farther from Jupiter than Io, so the tidal heating is less intense, not enough to melt rock, but sufficient to maintain liquid water beneath the frozen surface. The first hints of Europa's subsurface ocean came from the Voyager spacecraft, which revealed a surface remarkably free of impact craters. Like Io, Europa's lack of craters indicated a young surface, one that had been renewed relatively recently by geological processes. But unlike Io, Europa showed no signs of active volcanism. Instead, its surface was covered by a network of dark lines, cracks and ridges that crisscrossed the ice in complex patterns. The Galileo spacecraft, which arrived at Jupiter in 1995, provided much more detailed observations of Europa and strengthened the case for a subsurface ocean. Galileo's magnetometer detected a magnetic field around Europa that varied in response to Jupiter's rotating magnetic field, exactly the signature expected if the Moon contained a layer of electrically conducting fluid beneath its surface. The most likely candidate for this conducting layer was salty water, an ocean of brine hidden beneath the ice. The thickness of Europa's ice shell remains uncertain, with estimates ranging from a few kilometres to several tens of kilometres. Some regions of the surface show evidence of relatively thin ice, where the frozen crust has broken apart and refrozen in patterns reminiscent of sea ice on Earth. Other regions appear more stable, suggesting thicker ice that has remained intact for longer periods. The ice shell is not static. It appears to be slowly churning, with warmer ice rising from below and cooler ice sinking, a process called convection that helps transport heat from the ocean to the surface. The surface features of Europa tell the story of a world in constant, if slow, motion. The dark lines that crisscross the surface are ridges and fractures formed as the ice shell flexes in response to tidal forces. As Europa moves around its slightly elliptical orbit, Jupiter's gravitational pull stretches and compresses the Moon, causing the ice shell to crack and shift. Some of these cracks have opened and closed repeatedly, allowing material from below to well up and freeze on the surface, creating the distinctive double ridges that are among Europa's most common features. In some regions, the ice appears to have broken into large blocks that have shifted and rotated before refreezing in new positions. These chaotic terrains, as they're called, resemble the jumbled ice flows found in Earth's polar seas and suggest that the ice shell was thin enough in these areas to allow significant movement. The blocks can be fitted back together like puzzle pieces, revealing how much they have moved since they broke apart. Perhaps the most tantalizing features on Europa are the plumes of water vapour that may be erupting from cracks in the ice shell. The Hubble Space Telescope has detected what appear to be plumes rising from Europa's surface, similar to the geysers that erupt from Saturn's moon Enceladus. If confirmed, these plumes would provide a way to sample Europa's ocean without having to drill through the ice shell. A spacecraft could simply fly through the plume and analyse the material it contains. The possibility that Europa harbours a liquid water ocean has profound implications for the search for life beyond Earth. On our planet, life exists wherever liquid water is found, from boiling hot springs to frozen Antarctic lakes. If Europa's ocean is in contact with a rocky seafloor, as seems likely, then chemical reactions between water and rock could provide the energy and nutrients needed to support life. Hydrothermal vents on Earth's ocean floor support thriving ecosystems that are entirely independent of sunlight, deriving their energy from chemical reactions between seawater and hot rock. Similar vents might exist on Europa's seafloor, providing oases of warmth and chemistry in the cold, dark ocean. The prospect of life on Europa has made the Moon a high priority for future exploration. NASA's Europa Clipper mission, launched in 2024, will conduct detailed studies of Europa during dozens of close flybys, using radar to probe the ice shell, spectrometers to analyse the surface composition, and cameras to image the surface in unprecedented detail. The mission will help determine the thickness of the ice shell, the depth and salinity of the ocean, and whether conditions are favourable for life. Future missions may go even further, landing on Europa's surface and perhaps eventually drilling through the ice to explore the ocean directly. Such missions face enormous technical challenges, from surviving the intense radiation environment near Jupiter to penetrating kilometres of ice to designing instruments that can operate in an alien ocean. But the potential reward, the discovery of life beyond Earth, makes these challenges worth confronting. Even if Europa's ocean proves to be lifeless, the Moon would still be a fascinating world worthy of study. The processes that shape its ice shell, the chemistry of its ocean, the interactions between the Moon and Jupiter's magnetic field, all offer insights into planetary science that cannot be gained from studying Earth alone. Europa is a natural laboratory for understanding how icy worlds work, and the lessons learned there will inform our understanding of similar bodies throughout the solar system and beyond. As you drift towards sleep, imagine yourself descending through Europa's ice shell, passing through layers of frozen water that have accumulated over millions of years. The ice grows warmer as you descend, heated from below by the ocean's warmth. Finally, you break through into the dark waters beneath, a vast ocean that has never seen sunlight, where strange currents flow and unknown chemistry unfolds. What might live in these waters? What wonders might await discovery in this hidden sea? Let these questions carry you gently into dreams, where the boundaries between the known and the unknown dissolve like ice in warm water. Section 8. The Galilean moons, Ganymede and Callisto. Beyond Europa orbit the two largest of the Galilean moons, Ganymede and Callisto, worlds that share some similarities with their inner neighbours, but also possess their own unique characteristics. These outer moons are less affected by Jupiter's tidal forces than Io and Europa, resulting in surfaces that are older and more heavily cratered. Yet both Ganymede and Callisto harbour secrets of their own, including the possibility that they too may possess subsurface oceans hidden beneath their icy exteriors. Ganymede is the largest moon in the entire solar system, with a diameter of 5,268 kilometres, making it larger than the planet Mercury and nearly as large as Mars. If Ganymede orbited the Sun instead of Jupiter, it would easily qualify as a planet in its own right. This enormous moon orbits Jupiter at a distance of about 1,070,000 kilometres, completing one orbit every 7.15 Earth days. The surface of Ganymede is divided into two distinct types of terrain. About one-third of the surface consists of dark, heavily cratered regions that are among the oldest surfaces in the solar system, dating back nearly to the formation of the Moon itself, more than 4 billion years ago. These dark regions are saturated with impact craters, meaning that new craters can only form by destroying older ones, a sign of extreme antiquity. The remaining two-thirds of Ganymede's surface consists of lighter, younger terrain, marked by grooves and ridges rather than craters. This grooved terrain formed when the Moon's icy crust was stretched and fractured by internal forces, perhaps related to the freezing and expansion of a subsurface ocean or to tidal heating early in Ganymede's history. The grooved terrain is younger than the dark cratered regions, though still ancient by terrestrial standards, with ages estimated at 1 to 2 billion years. Ganymede is the only moon in the solar system known to possess its own internally generated magnetic field. This magnetic field, discovered by the Galileo spacecraft, is embedded within Jupiter's much larger magnetic field, creating a complex magnetic environment around the Moon. The existence of an internal magnetic field implies that Ganymede has a liquid, electrically conducting layer in its interior, most likely a core of liquid iron similar to Earth's outer core. But Ganymede may also possess a different kind of liquid layer, a subsurface ocean of water sandwiched between layers of ice. Unlike Europa, where the ocean is thought to be in direct contact with a rocky seafloor, Ganymede's ocean may be trapped between an outer shell of regular ice and a deeper layer of high-pressure ice that forms under the immense pressures found deep within the Moon's interior. Recent modelling suggests that Ganymede's internal structure might resemble a club sandwich, with multiple ocean layers separated by different phases of ice, and the lowest liquid layer potentially adjacent to the rocky mantle. This complex layering arises because water can exist in many different solid forms depending on pressure and temperature, and Ganymede is large enough that these exotic ice phases become relevant in its deep interior. The possibility that Ganymede's deepest ocean layer might be in contact with rock is encouraging for those who wonder about the Moon's potential to support life. Water-rock contact allows for chemical reactions that could provide energy and nutrients for living organisms, similar to the hydrothermal systems that support life in Earth's deep oceans. When researchers added salts to their computer models of Ganymede's interior, they found that the resulting brines could be dense enough to sink to the seafloor, maintaining contact between liquid water and rock even under the enormous pressures present at those depths. The extreme depths involved, roughly 800 kilometers to the rocky seafloor, mean that temperatures at the bottom of a convective ocean could be significantly higher than at the ice-water interface above. Ganymede may contain as much as 25 times the volume of water found on Earth, making it one of the most water-rich bodies in the solar system. This vast reservoir of water, combined with the Moon's complex internal structure and the possibility of water-rock interactions, makes Ganymede a fascinating target for future exploration. The European Space Agency's JUICE mission, which stands for Jupiter Icy Moons Explorer, will study Ganymede in detail when it arrives at Jupiter in the 2030s, eventually entering orbit around the giant Moon to conduct close-up observations of its surface, interior, and magnetic environment. The surface of Ganymede, while ancient compared to the geologically active surfaces of Io and Europa, still holds clues to the Moon's history and internal processes. The grooved terrain that covers much of the surface formed when the icy crust was stretched and fractured, creating parallel ridges and troughs that extend for hundreds of kilometers. These features may have formed during an early period of tidal heating, when Ganymede's orbit was more eccentric than it is today, or they may be related to the freezing and expansion of the subsurface ocean. Impact craters on Ganymede provide a record of the bombardment history of the outer solar system. The largest impact feature on Ganymede is a multi-ring structure called Valhalla, though this name is sometimes confused with a similar feature on Callisto. Ganymede's largest impact basin is actually called Gilgamesh, a massive scar roughly 600 kilometers in diameter that formed when a large asteroid or comet struck the Moon billions of years ago. The relatively shallow depth of this basin, compared to what would be expected for an impact of this size on a rocky body, reflects the ability of ice to flow and relax over geological time, gradually erasing the topographic signature of ancient impacts. Ganymede's thin atmosphere, composed primarily of oxygen, was detected by the Hubble Space Telescope in the 1990s. This tenuous envelope of gas is produced when charged particles from Jupiter's magnetosphere strike the icy surface, breaking apart water molecules and releasing oxygen atoms that briefly linger around the Moon before escaping into space. The atmosphere is far too thin to be breathable or to significantly affect the surface, but its presence adds another dimension to our understanding of this complex world. Now we turn to Callisto, the outermost of the Galilean moons and in many ways the most enigmatic. Callisto orbits Jupiter at a distance of about 1,883,000 kilometers, completing one orbit every 16.69 Earth days. At this distance, Callisto is far enough from Jupiter that tidal heating is negligible, and the Moon has remained geologically dead for most of its history. Yet Callisto, too, may harbour a subsurface ocean, a possibility that raises intriguing questions about how such an ocean could have formed and persisted without significant tidal heating. Callisto is nearly the same size as Mercury, with a diameter of 4,821 kilometres, making it the third largest moon in the solar system after Ganymede and Saturn's Titan. Its surface is the most heavily cratered of any body in the solar system, a testament to billions of years of bombardment uninterrupted by geological activity. Unlike Ganymede, Callisto shows no evidence of grooved terrain or other signs of internal activity. Its surface is uniformly ancient, a frozen record of the solar system's violent youth. The most prominent feature on Callisto is Valhalla, an enormous multi-ring impact basin that dominates one hemisphere of the Moon. Valhalla consists of a bright central region about 600 kilometers across, surrounded by concentric rings that extend outward for nearly 2,000 kilometers. These rings formed when the impact that created Valhalla sent shockwaves through Callisto's icy crust, fracturing the surface in a pattern of concentric circles. The relatively subdued topography of Valhalla, like that of large impact features on Ganymede, reflects the tendency of ice to flow and relax over time. Despite its ancient, cratered surface, Callisto may not be entirely frozen solid. Measurements by the Galilean spacecraft detected variations in Callisto's magnetic field that suggest the presence of a conducting layer beneath the surface, most likely a salty ocean similar to those inferred for Europa and Ganymede. This finding was surprising because Callisto experiences very little tidal heating, raising the question of how a subsurface ocean could remain liquid over billions of years. One possibility is that Callisto's ocean is maintained by the slow decay of radioactive elements in the Moon's rocky interior, which generates a small but steady supply of heat. Another possibility is that the ocean contains antifreeze compounds, such as ammonia, that lower the freezing point of water and allow it to remain liquid at temperatures that would freeze pure water. Whatever the explanation, the potential presence of an ocean on Callisto adds to the growing list of worlds in our solar system where liquid water may exist beneath icy surfaces. Callisto's lack of geological activity makes it an attractive target for future human exploration of the Jupiter system. Unlike the inner Galilean moons, Callisto lies outside the most intense regions of Jupiter's radiation belts, making it a relatively safe haven for astronauts and equipment. A base on Callisto could serve as a staging point for missions to Europa and the other moons, allowing humans to study the Jupiter system while minimizing their exposure to harmful radiation. The Moon's ancient stable surface would also provide a window into the early history of the solar system, preserving a record of conditions that have been erased elsewhere by geological activity. The 4 Galilean moons taken together represent an astonishing diversity of worlds. Io, with its continuous volcanic eruptions and sulphurous surface, is a world of fire and transformation. Europa, with its smooth ice shell and hidden ocean, is a world of water and possibility. Ganymede, with its grooved terrain and layered interior, is a world of complexity and scale. Callisto, with its ancient craters and quiet depths, is a world of stillness and memory. Each moon tells a different story, and together they demonstrate the remarkable variety that can arise even within a single planetary system. As you rest and let your thoughts drift among these distant worlds, imagine yourself travelling from moon to moon, experiencing the unique character of each. Feel the heat of Eo's volcanoes, the chill of Europa's ice, the vastness of Ganymede's grooved plains, the silence of Callisto's cratered highlands. These are worlds that humans may one day visit, places where future generations might walk and wonder and discover. For now, they remain distant points of light in our telescopes, but the knowledge we have gained about them brings them closer, making them real in our imaginations, even as they remain physically out of reach. Let the diversity of the Galilean moons remind you of the richness of our solar system, the countless worlds waiting to be explored, the endless possibilities for discovery that lie beyond our small blue planet. Rest now, knowing that the universe is vast and full of wonders, and that the journey of exploration has only just begun. Section 9. The Lesser Moons and Ring System. Beyond the 4 great Galilean moons, Jupiter is attended by a vast retinue of smaller satellites, a diverse collection of worlds ranging from tiny irregular fragments to substantial bodies with their own unique characteristics. As of the most recent counts, Jupiter has more than 90 known moons, more than any other planet in our solar system. These lesser moons fall into several distinct groups based on their orbits, sizes, and probable origins, and together they tell a story of capture, collision, and the complex gravitational dynamics of the Jupiter system. The innermost group of small moons orbits closer to Jupiter than Io, in a region where the giant planet's gravity and radiation create a harsh environment. These inner moons include Metis, Adrastea, Amalthea, and Thebe, all of which were discovered in the 20th century using ground-based telescopes or spacecraft observations. These moons are small, irregularly shaped bodies that orbit within or near Jupiter's faint ring system, and their surfaces are constantly bombarded by charged particles from Jupiter's magnetosphere. Amalthea, the largest of the inner moons, was discovered in 1892 by the American astronomer Edward Emerson Barnard, making it the first new moon of Jupiter to be found since Galileo's discoveries nearly 3 centuries earlier. Amalthea is an irregularly shaped body, roughly 250 kilometers long and 130 kilometers wide, with a dark, reddish surface that may be coated with sulfur compounds originating from Io's volcanic eruptions. The moon orbits Jupiter in just under 12 hours, faster than Jupiter itself rotates, and is gradually spiraling inward due to tidal interactions with the planet. Metis and Adrastea are even smaller than Amalthea, with diameters of only about 40 and 20 kilometers respectively. These tiny moons orbit at the outer edge of Jupiter's main ring, and their gravitational influence helps confine the ring particles to a narrow band. Thebe, slightly larger than Adrastea, orbits just outside the main ring and is associated with a faint outer ring called the Thebe-Gossamer ring. Jupiter's ring system, while far less spectacular than Saturn's famous rings, is a fascinating feature in its own right. The rings were discovered in 1979 by the Voyager 1 spacecraft, which detected a faint band of material encircling Jupiter during its flyby. Subsequent observations by Voyager 2, the Galileo spacecraft, and ground-based telescopes have revealed a complex ring system consisting of several distinct components. The main ring is a thin, relatively bright band about 6,500 kilometers wide, orbiting at a distance of roughly 122,000 to 129,000 kilometers from Jupiter's center. This ring is composed primarily of small dark particles, probably dust knocked off the surfaces of Metis and Adrastea by micrometeorite impacts. Unlike Saturn's rings, which are made of bright, icy particles, Jupiter's rings are made of rocky, silicate material that reflects very little light, making them difficult to observe from Earth. Inside the main ring lies the halo, a thick, faint torus of material that extends from the main ring down toward Jupiter's cloud tops. The halo is composed of very fine dust particles that have been drawn inward by electromagnetic forces and gravitational perturbations. These tiny particles are constantly being replenished by material from the main ring, as the dust slowly spirals inward and is eventually swept up by Jupiter's atmosphere. Outside the main ring lie two faint gossamer rings associated with the moons Amalthea and Thebe. These rings are extremely tenuous, visible only in images taken with long exposures or special viewing geometries. The gossamer rings are composed of dust particles ejected from Amalthea and Thebe by micrometeorite impacts, and they extend outward from each moon's orbit, forming broad diffuse bands that gradually fade with distance from Jupiter. The origin of Jupiter's rings is fundamentally different from the origin of Saturn's rings. Saturn's rings are thought to be either primordial, dating back to the formation of the planet, or the result of a relatively recent catastrophic event, such as the destruction of a moon or the capture and disruption of a comet. Jupiter's rings, by contrast, are clearly being continuously generated by the erosion of the inner moons. Without this constant replenishment, the rings would disappear within thousands of years, as the small particles that compose them are gradually swept up by Jupiter's atmosphere or ejected from the system by radiation pressure and electromagnetic forces. Moving outward from the inner moons and rings, we encounter a vast empty region before reaching the orbits of the Galilean moons. Beyond the Galilean moons lies another population of small satellites, the irregular moons, which follow distant, elongated, and often highly inclined orbits around Jupiter. These irregular moons are thought to be captured objects, asteroids or comets that wandered too close to Jupiter and were snared by the giant planet's gravity. The irregular moons of Jupiter fall into several distinct groups based on their orbital characteristics. The Himalaya group consists of moons with prograde orbits, meaning they orbit in the same direction that Jupiter rotates. These moons have orbital distances of roughly 11 to 12 million kilometers and orbital periods of about 250 to 260 Earth days. The largest member of this group, Himalaya itself, is about 170 kilometers in diameter and was discovered in 1904. Several other groups of irregular moons follow retrograde orbits, meaning they orbit in the opposite direction from Jupiter's rotation. These retrograde groups include the Ananke group, the Calm group, and the Pasiphae group, each named after its largest member. The retrograde moons are generally smaller and more distant than the prograde irregular moons, with some orbiting more than 20 million kilometers from Jupiter. Their retrograde orbits strongly suggest that they are captured objects, as moons that formed in place around Jupiter would be expected to orbit in the same direction as the planet's rotation. The capture of irregular moons is thought to have occurred early in the solar system's history, when Jupiter was still surrounded by a disk of gas left over from its formation. Objects passing through this gas disk would have been slowed by drag, allowing Jupiter's gravity to capture them into bound orbits. Once the gas disk dissipated, capture became much more difficult, so most of Jupiter's irregular moons were probably acquired during the first few 100 million years of the solar system's existence. Many of the irregular moons are probably fragments of larger parent bodies that were broken apart by collisions after being captured. The clustering of irregular moons into distinct orbital groups supports this hypothesis, as the members of each group may be the remnants of a single captured object that was subsequently shattered. The ongoing discovery of new irregular moons, made possible by increasingly sensitive telescopes and survey techniques, continues to reveal the complexity of Jupiter's satellite system. The total mass of all the irregular moons combined is tiny compared to the Galilean moons, amounting to less than 1% of the mass of even the smallest Galilean satellite. Yet these small distant objects provide valuable information about the conditions in the early solar system and the processes by which giant planets acquire their satellite systems. Each irregular moon is a messenger from the past, a fragment of the primordial solar system preserved in the cold depths of Jupiter's gravitational embrace. As you rest and contemplate Jupiter's extensive family of moons, imagine the view from one of these distant, irregular satellites. Jupiter would appear as a bright disk, its bands and storms visible but small, while the Galilean moons would be mere points of light tracing their endless orbits around the giant planet. The sun would be a distant star, providing little warmth to these frozen outposts. Yet even here, in the cold and dark at the edge of Jupiter's realm, there is wonder to be found, stories written in the orbits and compositions of these captured wanderers. Let the vastness of Jupiter's satellite system remind you of the scale of our solar system, the countless worlds that orbit our sun, each with its own history and its own secrets. Rest now, knowing that even the smallest and most distant of these worlds has something to teach us about the universe we inhabit. Section 10, Spacecraft Exploration, Pioneer to Galileo. The story of Jupiter's exploration by spacecraft begins in the early 1970s, when humanity first sent robotic emissaries across the vast gulf of space to study the giant planet up close. These pioneering missions transformed our understanding of Jupiter, revealing details that could never be discerned from Earth, and raising new questions that continue to drive exploration to this day. The journey from the first tentative flybys to sophisticated orbital missions represents one of the great achievements of the space age. Pioneer 10, launched on March 2, 1972, was the first spacecraft designed to travel through the asteroid belt and visit Jupiter. The mission was a bold venture into the unknown, as scientists were uncertain whether a spacecraft could survive the passage through the asteroid belt, where collisions with debris might prove fatal. Pioneer 10 carried a modest suite of instruments to study Jupiter's magnetic field, radiation environment, atmosphere, and moons, along with a gold-plated plaque depicting a man and woman and the location of Earth in case the spacecraft was ever found by extraterrestrial beings. Pioneer 10 reached Jupiter on December 3, 1973, passing within 130,000 kilometers of the planet's cloud tops. The spacecraft returned the first close-up images of Jupiter, revealing the banded structure of the atmosphere and the swirling storms in unprecedented detail. Pioneer 10 also made the first direct measurements of Jupiter's intense radiation belts, discovering that the radiation environment near the planet was far more severe than anticipated. The spacecraft received a radiation dose that would have been lethal to a human astronaut, demonstrating the challenges that future missions would face. Pioneer 11 followed its twin to Jupiter, launching on April 5, 1973, and arriving at the planet on December 2, 1974. Pioneer 11 took a different trajectory than its predecessor, passing much closer to Jupiter and using the planet's gravity to redirect its course towards Saturn. This gravity assist maneuver, one of the first of its kind, demonstrated a technique that would become essential for exploring the outer solar system. Pioneer 11 returned additional images and data from Jupiter before continuing on to its historic encounter with Saturn in 1979. The Pioneer missions were followed by the Voyager spacecraft, which represented a significant leap forward in capability and ambition. Voyager 1 and Voyager 2, launched in the summer of 1937, carried far more sophisticated instruments than the Pioneers, including high-resolution cameras capable of returning detailed images of Jupiter and its moons. The Voyagers took advantage of a rare alignment of the outer planets, that occurs only once every 125 years, allowing a single spacecraft to visit multiple planets using gravity assists. Voyager 1 arrived at Jupiter on March 5, 1979, beginning an intensive period of observation that would revolutionize our understanding of the Jupiter system. The spacecraft's cameras returned thousands of images, revealing the intricate structure of Jupiter's atmosphere, the active volcanoes of Io, the fractured ice surface of Europa, and the cratered landscapes of Ganymede and Callisto. The discovery of active volcanism on Io was one of the most significant findings of the entire Voyager mission, demonstrating that geological activity was not limited to large rocky planets like Earth. Voyager 1 also discovered Jupiter's ring system, a faint band of material that had escaped detection from Earth. The spacecraft's instruments measured the composition and structure of Jupiter's atmosphere, mapped the planet's magnetic field, and studied the interactions between Jupiter and its moons. After completing its Jupiter encounter, Voyager 1 continued on to Saturn before heading out of the solar system entirely, carrying its famous golden record containing sounds and images from Earth. Voyager 2 arrived at Jupiter on July 9, 1979, 4 months after its twin. The second spacecraft followed a different trajectory, allowing it to observe features that Voyager 1 had missed and to study changes that had occurred in the intervening months. Voyager 2's observations of Io revealed that the moon's volcanic activity had changed significantly since Voyager 1's flyby, with some eruptions ceasing and new ones beginning. This demonstrated that Io's volcanism was not a static phenomenon, but a dynamic process that varied on timescales of weeks to months. After Jupiter, Voyager 2 continued on to Saturn, Uranus, and Neptune, becoming the only spacecraft to visit all 4 giant planets. The data returned by the Voyager missions filled volumes and transformed our understanding of the outer solar system. Decades later, both Voyager spacecraft continue to operate, now exploring the boundary between the solar system and interstellar space, still sending back data from the most distant reaches ever explored by human-made objects. The next major mission to Jupiter was Galileo, a spacecraft designed not merely to fly past the planet, but to orbit it, conducting long-term observations of Jupiter and its moons. Galileo was launched on October 18, 1989, aboard the Space Shuttle Atlantis, beginning a 6-year journey to Jupiter that included gravity assists from Venus and Earth. Galileo arrived at Jupiter on December 7, 1995, becoming the first spacecraft to orbit the giant planet. On the same day, an atmospheric probe that had been released from the main spacecraft 5 months earlier plunged into Jupiter's atmosphere, returning data on the composition, temperature, pressure, and wind speeds of the upper atmosphere before being crushed by the increasing pressure at depth. The atmospheric probe descended through Jupiter's clouds for about an hour, transmitting data until it reached a depth where the pressure exceeded 22 bars, more than 22 times the atmospheric pressure at Earth's surface. The probe measured wind speeds that increased with depth, reaching over 600 kilometers per hour, and found that Jupiter's atmosphere was drier than expected, with less water vapor than models had predicted. This finding puzzled scientists, who later realized that the probe had descended into an unusually dry region of the atmosphere, a hot spot where descending air had depleted the water content. The Galileo orbiter spent nearly 8 years studying Jupiter and its moons, completing 34 orbits of the planet and conducting close flybys of all 4 Galilean moons. The spacecraft's observations transformed our understanding of these worlds, providing evidence for subsurface oceans on Europa, Ganymede, and Callisto, mapping the volcanic activity of Io in unprecedented detail, and revealing the complex interactions between Jupiter's magnetic field and its moons. Galileo's camera returned thousands of images, showing features as small as a few tens of meters across on the surfaces of the Galilean moons. The spacecraft's magnetometer detected the magnetic signatures of subsurface oceans, while its spectrometers mapped the composition of the moon's surfaces. Galileo also observed the impact of Comet Shoemaker-Levy 9 into Jupiter in July 1994, providing a unique perspective on this historic event from its position en route to the planet. The Galileo mission faced significant challenges, including the failure of its high-gain antenna to fully deploy, which severely limited the amount of data that could be transmitted back to Earth. Engineers worked around this problem by using the spacecraft's low-gain antenna and developing new data compression techniques. But the total data return was still far less than originally planned. Despite this setback, Galileo returned a wealth of scientific information that continues to inform our understanding of the Jupiter system. The mission ended on September 21st, 2003, when Galileo was deliberately plunged into Jupiter's atmosphere to prevent any possibility of the spacecraft contaminating Europa with Earth microbes. This planetary protection measure reflected the growing recognition that Europa might harbour conditions suitable for life, and that we have a responsibility to protect potential extraterrestrial ecosystems from contamination by terrestrial organisms. The legacy of the Pioneer, Voyager and Galileo missions extends far beyond the data they returned. These spacecraft demonstrated that humanity could explore the outer solar system, sending robotic emissaries across billions of kilometers to study worlds that had previously been mere points of light in our telescopes. They revealed Jupiter and its moons as complex, dynamic worlds worthy of continued exploration, and they laid the groundwork for the missions that would follow. As you rest and reflect on these journeys of exploration, imagine the spacecraft as they cross the vast emptiness between Earth and Jupiter, their instruments patiently gathering data, their cameras capturing images of worlds no human eye had ever seen up close. These machines, built by human hands and guided by human minds, extended our senses across the solar system, allowing us to experience the wonder of Jupiter without leaving our home planet. Let the spirit of exploration that drove these missions inspire your dreams, carrying you to distant worlds where discovery awaits. Section 11. Modern Exploration, Juno and Beyond. The exploration of Jupiter entered a new era on July 4, 2016, when the Juno spacecraft fired its main engine and slipped into orbit around the giant planet. Juno represented a different approach to studying Jupiter than its predecessor Galileo, focusing on the planet itself rather than its moons, and using a highly elliptical polar orbit that allowed it to pass closer to Jupiter's cloud tops than any previous spacecraft. Juno's primary mission was to study Jupiter's interior structure, magnetic field, and atmospheric dynamics, addressing fundamental questions about how the planet formed and evolved. The spacecraft carries a suite of instruments designed to peer beneath Jupiter's clouds, including a microwave radiometer that can sense thermal radiation from deep within the atmosphere, a gravity science experiment that measures tiny variations in Jupiter's gravitational field, and a magnetometer that maps the planet's magnetic field with unprecedented precision. The spacecraft's polar orbit takes it from high above Jupiter's North Pole, down across the equator at an altitude of only about 4,000 kilometers above the cloud tops, and then back up over the South Pole. This trajectory allows Juno to study Jupiter's polar regions, which had never been observed closely by previous missions, and to sample different longitudes on each orbit as the planet rotates beneath the spacecraft. One of Juno's most striking discoveries has been the revelation of Jupiter's polar cyclones, the geometric arrangements of storms that cluster around the planet's north and south poles. At the North Pole, a central cyclone is surrounded by 8 smaller cyclones arranged in an octagonal pattern, while at the South Pole, a central cyclone is encircled by 5 peripheral cyclones forming a pentagon. These cyclone clusters were completely unexpected and have challenged scientists to explain how they formed and why they maintain their stable configurations. Juno's microwave radiometer has provided new insights into the structure of Jupiter's atmosphere, revealing that the colourful bands visible at the cloud tops extend deep into the planet, persisting to depths of at least 3,000 kilometres. This finding indicates that Jupiter's atmospheric circulation is not a shallow phenomenon confined to the upper layers, but a deep-seated process that involves a significant fraction of the planet's mass. The ammonia distribution in Jupiter's atmosphere has proven to be more complex than expected, with variations that suggest vigorous mixing and transport processes. The gravity science experiment has revealed that Jupiter's interior is not as simple as earlier models suggested. The data indicate that Jupiter's core is not a compact ball of rock and ice, but rather a dilute or fuzzy core that extends over a large region and is mixed with the surrounding hydrogen and helium envelope. This finding has implications for how Jupiter formed, suggesting that the planet may have experienced a giant impact early in its history that disrupted an originally compact core, or that the core never fully differentiated in the first place. Juno's magnetometer has mapped Jupiter's magnetic field in unprecedented detail, revealing a field that is far more complex and irregular than Earth's relatively simple dipole field. Jupiter's magnetic field has strong localized anomalies, regions where the field is much stronger or weaker than the surrounding areas, suggesting that the dynamo generating the field operates differently than Earth's dynamo. The field is also asymmetric, with the magnetic equator shifted northward from the geographic equator. The spacecraft has also studied Jupiter's auroras, capturing stunning images of the glowing polar lights in ultraviolet and infrared wavelengths. Juno's observations have revealed that Jupiter's auroras are powered by different processes than Earth's auroras, with much of the energy coming from within the Jupiter system itself rather than from the solar wind. The volcanic moon, Io, plays a crucial role in powering Jupiter's auroras, as material ejected from Io's volcanoes becomes ionized and trapped in Jupiter's magnetic field, eventually precipitating into the atmosphere and producing auroral emissions. Juno's extended mission has expanded the spacecraft's objectives to include studies of Jupiter's moons and rings. The spacecraft has conducted close flybys of Ganymede, Europa, and Io, returning detailed images and data that complement the observations made by earlier missions. These flybys have revealed new details about the moon's surfaces and interiors, including evidence for shallow subsurface water on Europa and ongoing changes in Io's volcanic activity. Looking beyond Juno, the future of Jupiter exploration is bright, with several major missions planned or in development. NASA's Europa Clipper mission, launched in October 2024, will conduct a detailed investigation of Europa, the moon that many scientists consider the most promising place to search for life beyond Earth. Europa Clipper will make dozens of close flybys of Europa, using radar to probe the ice shell, spectrometers to analyse the surface composition, and cameras to image the surface in high resolution. The European Space Agency's JUICE mission, launched in April 2023, will study Jupiter and its icy moons, with a particular focus on Ganymede. After arriving at Jupiter in 2031, JUICE will conduct flybys of Europa and Callisto before entering orbit around Ganymede in 2034, becoming the first spacecraft to orbit a moon other than Earth's moon. JUICE will study Ganymede's surface, interior, and magnetic field, searching for evidence of the subsurface ocean and characterizing the moon's potential habitability. Future missions may go even further, landing on Europa's surface or even penetrating the ice shell to explore the ocean beneath. Such missions face enormous technical challenges, from surviving the intense radiation environment near Jupiter to drilling through kilometers of ice to designing instruments that can operate in an alien ocean. But the potential rewards are immense. The discovery of life beyond Earth would be one of the most profound scientific findings in human history, transforming our understanding of our place in the universe. Other concepts for future Jupiter exploration include atmospheric probes that would descend deeper into Jupiter's atmosphere than the Galileo probe, studying the transition from gas to liquid and searching for the water clouds that are thought to exist at depth. Balloon missions that would float in Jupiter's atmosphere for extended periods have also been proposed, allowing long-term study of the planet's weather and atmospheric chemistry. The exploration of Jupiter is far from complete. Each mission has answered some questions while raising new ones, and the giant planet continues to surprise us with its complexity and dynamism. The storms that rage in its atmosphere, the oceans that may hide beneath its moon's icy surfaces, the magnetic field that extends millions of kilometers into space, all of these phenomena invite further study and promise new discoveries. As you rest and contemplate the ongoing exploration of Jupiter, imagine the spacecraft that are even now traveling through the darkness of space, their instruments ready to capture new data, their cameras poised to reveal new wonders. The journey of discovery that began with Galileo's telescope continues today, carried forward by the robotic emissaries we send to explore on our behalf. Each mission builds on the work of those that came before, adding new pieces to the puzzle of Jupiter and bringing us closer to understanding this magnificent world. Let the spirit of exploration that drives these missions inspire your dreams, carrying you to the frontiers of knowledge where the unknown awaits. Rest now, knowing that the quest to understand Jupiter and its moons continues, and that the discoveries yet to come may be even more remarkable than those we have already made.